So the final part I would like to discuss the binary search recursive algorithm is to argue about its running time. But the issue is we cannot really apply what we learned from week number 1 and 2 because there's simply no loops over here. But we got recursion, we got recursive call. You can see the recursive call number 1, recursive call number 2. So whatever we learned back in week number 1 and week number 2 does not seem to be applicable over here. But it's not quite true. I think we're missing some bridge over here to really try to formulate some mathematical equation, and we'll try to do some unfolding. Once we get to that point, we will be able to apply what we learned from week number 1 and 2. So I'm going to show you how to build that bridge. Right? Let's now see how exactly we can do it. Right? So to talk about the recursive algorithm like a binary search, before I do that, I would like to talk about one simple exercise just to warm up. Right? That will be also very useful for our derivation of the running time for recursive algorithm. Right? Let's now talk about it. And this is a fragment of code which I taught in the earlier OOP course in 2030 when I spoke about how you can actually run recursion on the array. So this is considered as basic for this course, but for this one here, it's simply try to determine whether or not in the input array, if all the numbers are positive, right? We simply invoke the recursive helper method over here. You can see here, the search space is the entire array over here, right? Agree? And then we simply say over here, we say from larger than 2, from equals 2, and etc. Right? So let's now talk about each individual cases quickly. And for the detailed tracing or detailed explanation about example like this, I will encourage you to really go back to the background study I mentioned about. You can definitely see details from there. I believe I also spoke about this particular recursive helper method as one of the last few examples, something like that. Okay. So we just have to know about the base cases and recursive cases. When from index is strictly larger than the 2 index. So for example like this, you can see from is strictly larger than 2. One example would be, let's say from is actually 3 and 2 is actually 4. That example. In that case, we are really talking about an interval like this to go from, I said it opposite way. From could be strictly larger than, so maybe from 4 to 3. In that case, if you got from 4 to 3, in that case, how many numbers do we actually have in this interval? By definition, it should be that the from is less than or equal to the 2 number. But if that's not the case, if from is strictly larger than 2, in that case, 0 numbers. Has 0 numbers. So that's why we say it's an empty range, right? In the case of it's empty range, we simply do this one over here. How much does it cost in the base case over here? It's simply return statements, so that'll be bigger of 1, right? Let me analyze this line. You know how to do that, right? The second base case we have is when from is actually equal to 2. That's the second base case over here. The second base case is when from is exactly equal to 2. For example, let's say we got from 3 and 2, also 3. In that case, how many numbers do we have in this particular interval? Has exactly just 1 number, right? So in that case, what was the running time? Also return statements, and also array indexing, and also some relational operation. It would be bigger of 1, right? So far, so good. Let's now take a look at the recursive case over here. And for the recursive case, let me use a different color here. So this will be the recursive case. In that case, what we do is we try to do from plus 1. We try to narrow down the space. We'll narrow down the problem size that we want to solve recursively. So you can see you can think about used to be this particular range that we wanted to start with. And however, we decide to recur on this subproblem over here from plus 1 all the way until 2. Right, you can see this part over here is really a strictly smaller problem that we are trying to solve. Right, let me just highlight it quickly. Okay, let me just do this. So you can see this part over here is really a strictly smaller problem to recur. Okay, let me just color that quickly. But it's a strictly smaller problem over here. Okay, so the pink one over here is really a strictly smaller problem. And in that case, we actually go from plus 1 to 2, right? Go from plus 1 to 2, right? How do we, also, how much time does it really cost to really do the recursion? You can see recursion itself is okay, but what about apart from the recursion? We also got to do some logical operation over here, and also some return, and also some relational operation over here as well. In that case, it would just be big of 1, right? So apart from the recursive call, it's like a recursive call combined with some bigger of 1 operation. So this part over here, let's write it down. This part over here is really big O of 1. And we're going to formulate the so-called recurrence relation to represent the running time, right? Recurrence relation. And only after we can formulate this recurrence relation can we actually try to unfold it and try to apply what we learned in week number 1 and 2, right? That's all we can do. Recurrence relation is really important. And what are they, right? Based on what we have analyzed so far. So here are the recurrence relation. It's a function called t over here, okay? T, and also t over here. And what's inside the t is the input size over here. Or you can think about the range of indices or range of the array size that you have to consider. So we got 3 cases. 0, empty array, empty range, and also we got 1. That means only the range of 1 number, right? 0 number, 1 number. And also we got over here is actually n over here, right? You can see the n over here. You can see the n over here. And that one there is really about the input size, really, because we got to recur by just reducing the size by 1. So these are the 3 equations we have to define, right? In this case, if it is the base case, what's the running time? It's actually big O of 1. So that's why we put 1 over here. What about the second base case, when the input range is actually 1? In that case, we put is also big of 1. So that's why we also put 1 over here. And what about the recursive case over here? For the recursive case, this part over here is really the sub-problem of size n minus 1. So this is really specifying the sub-problem of size n minus 1. You can think about if this is the original problem of size n. And this over here is the sub-problem of size n minus 1. Right? That's we're just reducing 1 number from here. All right. So how do we formulate this? The way to do it is we can say that it's going to be some recursive call t of size n minus 1. You can think about this n minus 1 over here is really corresponding to this n minus 1 over here is really corresponding to the range over here from plus 1 to 2. Right? That's the problem size of sub-problem of size n minus 1. And the 1 over here, right, is really about a big O of 1. That's apart from, in addition to the recursive call. 1 is the 1 over here. All right. Let me recap very quickly, and we still haven't really solved this recurrence relation over here. But it's really important for you to know how to formulate this recurrence relation based on the code of Java, of the recursive algorithm. Right? You need to consider base cases, in which case you got t of 0 and else t of 1. And exactly over here is about the big O of something, of that particular branch. Right? You can see it's big O of 1. That's why you put 1 over here. And for this part here, it's also big O of 1. So that's why you put 1 over here. And for t of n. So that would be to say if we actually try to consider the from to 2 over here, right? You can think about this is the original problem size to go from to 2, right? So that's exactly the outside box that I try to draw. And then in order to do that, we actually need to solve this strictly smaller problem over here. In that case, it will be from plus 1 to 2. So that will be exactly reducing the size by 1. So that will be t of n minus 1 plus any additional work you have to do in the recursive case. In that case, it's also big O of 1, as we actually argue. Right? So try to really see the close relationship between deriving the recurrence relation from the code itself. We'll do such exercise for all the recursion example we do. But make sure you learn about how to do it by yourself too. All right, so that's about the recurrence relation, and now we need to see how to solve it. Let me try to solve it over here. Okay, so this is really the recurrence relation we just derived from the last part, right? Let me just mention that. So this is the recurrence relation derived from the Java implementation of recursive algorithm. And you're going to know how to formulate such recurrence relation for every recursive Java code you're given, right? Now, how do we solve it, right? Let me show to you. And the principle is actually easy. The principle itself is easy, but to do it, you got to be careful. It's called unfolding. How do I exactly do unfolding? Let me show you. Right, so we're going to start with T of n. Right, you can see T of n over here, right? By definition, it is equal to T of n minus 1 plus 1. Right, so for this part here, it's just by applying this definition over here, right? And now you can see that we got n minus 1 over here in here. So we can simply use this n minus 1 as the n over here and try to unfold. Right? Let's now try to take a look. So what I can do is I can say it's going to be what would be the running time over here when n is replaced by n minus 1. It's going to be t of n minus 1 minus 1 and then plus 1. Right? It's going to be something like this. It's going to be, let's see, t of over here n minus 1 minus 1 and then plus 1. Right? I try to be as explicit as possible. You can see here, in order to calculate this one over here, we actually need to actually for this one over here, we simply substitute n over here by n minus 1. So that's why we got this part here substituted by n minus 1. So we got n minus 1 minus 1 and then plus 1 and plus 1 over here. But this part over here is about the t of n minus 1. Just this part over here. You got to study this very carefully. This part over here is the t n minus 1, right? But don't forget about this particular plus 1. So you got to say plus 1 over here. All right, are you okay so far? All right, hopefully you're okay so far. Let's do one more unfolding, right? Let's say we want to unfold. Let's say, how about this one here? Let's say we want to unfold. This part here is actually n minus 2. Agree? This part over here, let's simplify it. It's actually n minus 2. Right? How do we unfold t of n minus 2? Let's try to do that. Right? It's going to be t of over here, right? Just this part that we want to replace, right? Just this part. T of n minus 2. Over here, just this part. And don't forget, whatever result you got, you should still say plus 1 and plus 1, right? Just don't forget, right? For this part, how do we replace it? We're going to do the same exercise over here. So we're going to use the n minus 2 over here, substitute it for n. So here we're going to get n minus 2 minus 1, and then plus 1. That's what we're going to do, right? Let's try that. It's going to be t of, so we got n minus 2 over here, and then minus 1, and then plus 1. This part over here is just the t of n minus 2 alone, right? T of n minus 2 alone. And then we're going to say plus 1 and plus 1. Don't forget about these two. And plus 1, right? And now I can give you some hints about the pattern that we can observe from this, right? Let me use the pink over here. You can see this guy over here is really n minus 3. Right? You can see that, right? Alrighty. Now, can you observe any pattern over here? Because eventually, we can definitely keep unfolding this indefinitely. But our goal is we really want to see how many times do we really have to unfold like this until we can actually reach the base case. For example, this particular base case, we want to know that, right? Can you just by looking at this unfolding here, so this is the original recurrence relation for n, and this is with one unfolding, this is with two unfoldings over here, right? So now we want to know exactly how many times, how many unfoldings we need when we before we can get into t of 1. That's really the question. All right. You can now pause the video and think about it before I tell you the answer. Alrighty, assuming that you thought about it, right? Let me just give you some hints number 1 over here. You want to take a look at how many plus 1 we have over here. You can see here we got only a single plus 1 when we got minus 1, right? Here we got 2 plus 1s over here when we actually got a minus 2 over here, right? So here we got 3 plus 1 over here when we actually got n minus 3. This is really the pattern you can observe. Of course, I knew the solution, so that's why I can tell you how you should observe it. But that's some exercise you want to do, right? So whatever minus over here, minus 2, minus 1, and minus 3, the absolute value for that is going to correspond to how many plus 1 you have, right? For minus 1, you got plus 1. For minus 2, you got plus 2. For minus 3, you got plus 3. So what we want is, we want this pattern to really continue, right? Dot, dot, dot. The final line we should really expect to see is this. We want to have t of 1. That's something we want to get into, so we don't have to unfold any further. Because once you get to the base case, you definitely don't have to unfold any further. In this case, you can either try 1 or you can try 0, but in this case, it doesn't matter because it will be equal to 1 anyway. All right? And the question is, how many plus 1 do we actually have? Plus 1 and plus 1 all the way to plus 1, right? But now the question is, how many plus 1 do we really have over here? How many? That would be really the absence about unfolding exercise. I would say the most tricky part about unfolding is you have to make sure you actually perform the first few unfolding precisely by being very faithful to the application over here by definition. And number 2, you have to be able to observe the general pattern to know exactly how many times, how many unfoldings you will need to really get to the base case. That's also what we need to do for binary search, merge sort, and also quick sort, and also Tower of Hanoi if we got time later. All right, how many? Well, little hints over here. You may just want to rewrite this one over here in terms of the pattern that we actually concluded, right? Minus 3, minus 2 over here, and also minus 1 over here. 1 is simply n minus n. Oh, sorry, beg your pardon. It's simply n minus 1. Do you agree? Right? This is very important, actually, rewriting that that I'm trying to do over here. 1 is simply equal to n minus 1. So you can see n minus 1 over here should be about how many plus 1 we have based on our pattern. So the answer will be n minus 1. So the running time, so that means the running time t of n over here, it should be equal to n minus 1 over here plus t of 1 over here. As we know, is the base case already. So we know t of 1 by definition is also 1, right? This part over here is actually just 1, right? Plus 1, which is equal to just n, right? So that means the algorithm itself is big O of n. This definitely should make sense because this is simply just a linear algorithm over here to really go through the array. starting from the entire range of the array and keep reducing the size of the search space by 1 until we may just reach the final one to decide whether all the numbers are positive. So eventually, in the worst case, we have to look through all the numbers in the array. So that means it's linear. Alrighty, guys, I know it might be a very new idea to you. Let me recap very quickly. So this is only a warm-up exercise we're doing, and we're going to do this similar exercise as well for many times following this part. Let me just recap very quickly. You should really know about how to analyze the code for some recursive algorithm, talking about the base cases and fill out the input for the running time function about the input size and the corresponding runtime over here, right? And over here, the number, you don't really need to fill in the exact number of primitive operation. You don't need to be that precise. All you need to do is, if it's actually bigger of 1, in these two cases, you just put 1 over here. And then for the recursive case over here, you want to think about how many recursive how many recursive call I'm making. In this case, I'm only making one recursive call. So that means I'm only making one recursive function over here. So t of n is defined as t of n minus 1. So that's why the reason that is n minus 1 is actually derived from, we just go from plus 1 to 2. If you can see the visual diagram here, that's simply the subproblem of strictly smaller size, just reduced by 1. And then the 1 over here is any additional efforts you have to compute over here. In that case, it will simply just be the return, array indexing, and relational expression, right? That's the first part about formulating the recurrence relation. The second part over there, in which case we work very hard to actually get it, right? In that case, you really have to start with the general recurrence relation over here and keep unfolding for a few. Try to do a few unfoldings and observe the pattern to see all the constants that need to be added up. And then eventually you want to argue that if I reach this particular base case, how many turns exactly do I need in order to add up all the constant turns over here plus 1, right? That's going to be the principle you have to follow for all the unfolding exercises. It will be required if you want to calculate the recursive running time, right? Alrighty, so that's about the warm-up exercise, and let's now move on to doing the actual running time analysis for the binary search.